Hello, good evening, everyone. Nice to see all your. Well, I don't really see your faces, but nice to chat to you anyway. After what was no doubt a fairly, just turning the mic up, what was no doubt like a fairly stressful time this morning for those who were around for the UNSW power outage, whether you were at UNSW or whether you were just trying to use UNSW resources. Sorry, I guess, for any stress that was caused there. I wasn't particularly responsible for the outage. I assume everyone who's kind of watching this lecture is either watching it after the assignment's due or alternatively, they're already aware about the extension. But we did extend the assignment to 2 p.m. on Tuesday. So that's a little bit of extra time for everyone. Should take the pressure off a little bit. I guess I do want to apologize in advance for the problem with outages like this is that it inevitably means that some students who are doing the assignment on VLab or through the VS Code server or something that's like not local. Technically, it's like you kind of lose a little bit because other people could work on it for a few hours today, and I know that doesn't really make any massive difference, but I don't love things that don't feel fair sometimes, so sorry about that. It's one of those life things, but we kind of get on with it. Um, but yeah, today we're pretty much just going to start a new kind of round of content, um, which is here, where we're going to. So there's a bunch of topics over the next 4 weeks, which are essentially all about templates and iterators. And then there's some more advanced topics around C++ types and stuff. And essentially, this is all about assignment 3. We're really tying together the last parts of C++ that we teach in this course. And most of it falls around an idea of polymorphism in relation to classes, often, not always classes, and also a little bit of, you know, I guess iterators. So now, like this one we'll talk about on tomorrow night. It's like iterators. You're all kind of familiar with STL iterators, and that's why we talk about actually making your own. But today we're going to be talking about templates or C++ templates. Super interesting. This is one of my favorite topics. I don't know why. I couldn't give you a good reason why it's one of my favorite topics. It just is one of my favorite topics. I think it's just kind of interesting personally. But this topic about templates is all about understanding what we call compile time polymorphism or static polymorphism. And templates are something that you probably have a vague idea about because of, maybe working with a language like Java or something where you have like an array list or a linked list. But we're going to get into some more detail and learn more importantly about how this works with C++ or how it works with a language like C++. So we're going to be talking about templates, non-type parameters, exclusion principles, classes, statics, and friends, all in the context of templates as well. So first thing, polymorphism. You might have heard this word in another course. What does polymorphism mean? Well, polymorphism is providing a single interface to entities of different types. Often this is talked about when it comes to classes. If I use like a Java example here, where you say something in Java, like if you say you have a class like an animal, like you have an animal class in Java, and then you have another class that's like, say, dog that extends animal, and you have another class like a cat that extends animal. In Java, we would say that you could do something like animal D equals new dog, like this, and animal C equals new cat. And you could kind of, use polymorphism to allow you to refer to these subtypes as like a supertype. And the idea here is that you have these multiple types, like animals, cats, and dogs, that you can interact with via a common interface, which in this case is the interface of animal. So again, you know that if animal has a public function that returns a string called getName, and it can just return hello, like this. then you can call d.hello and d.getName and c.getName because it's using a common interface. So that's all polymorphism really is, because it's meant to be assumed knowledge according to the CSE programs. We don't really need to go into that in excessive depth. But what is an important distinction that's very different with C++ is that in C++ there are two types of polymorphism we're focused on. One is called static polymorphism and the other one is called dynamic polymorphism. Now, static polymorphism means that it is polymorphic at compile time, right? Static means at compile time. If you're statically analyzing your code, you're doing it before it compiles. If you're dynamically analyzing your code, it's happening while the program's running. So dynamic polymorphism is a kind of polymorphic thing where it's happening as your program runs. And that's actually what's happening in Java most of the time. So if you've done a course, like if you've learned a language like Python or Java, which are probably the two most likely object class-based languages that have polymorphism that you've likely dealt with, then often you have probably dealt with dynamic polymorphism. In the case of Python, it's because Python's a runtime, thing. In the case of Java, it's because it does its polymorphism at runtime, even though it is a compiled language. So static polymorphism, all that means is that we resolve the common interface at compile time. Because my point here in this other example is that we have this code, and when you say, animal D equals new dog, and then you say d.getName, how does this code figure out what function to call? Because D is of type animal, but it kind of points to a dog. So it's like, how does it do all that figuring out what it should call? How does it deal with that polymorphism? And the point is, it deals with that as the program's running. So it deals with that at runtime. C++, it can deal with it at runtime, and it can deal with it at compile time. And the first part of this lecture, templates, is dealing with it at compile time. And it's basically a form of function overloading. This all falls into a broader bucket of what we call generic programming, which is just about generalizing software components. And in fact, you've been dealing with templates since the start of the course, because that's exactly what all these types you've been using are, like STL containers. They're all just classes that you say, I have a vector of ints, I have a list of strings, I have an unordered set of ints and doubles. Like, these are all templates. That's all static polymorphism. What we're talking about now is actually making those ourselves. So before we get into class templates, which is really the bulk of where this is, it's really important to understand this idea of static polymorphism and essentially just like what it actually means in terms of compilation. So normally, if you have a function like a min function that can take in two ints or two doubles, and you want to have those two separate use cases, right, where it takes in two ints or two doubles, you would say create a function like this: auto min two ints returns an int, auto min double returns a double. Now you kind of have to do this in a way, because if you want a function that returns the min of two doubles, you want it to return a double, right? And if you have a function that wants let me load this up in VS Code. It'll be easier if I talk to the code. Yep, here. So this here. Now, ideally, you could maybe just do this, right? We could have a program that does this. It's just a function, takes in two doubles and returns a double. I could build it. I could run it. And yeah, if I try and run it, demo. Oh, I forgot the build. That's what happens when you do a flex week. I forget how to code. Demo 701, right? 1 and 1. Now, in reality, this is returning us a double, and it's just printing without the decimal point. But what happens if I don't want to return a double, right? I don't want that. I don't want to deal with floating point errors. I don't want to deal with like potentially a larger data type. So if I want a case where like comparing two ints, just gives me an int, that's why I use function overloading. Function overloading, fairly standard concept, most languages. We should get that, hopefully. Where things get slightly more tricky is when we start then looking at function templates, which is the next slide, looking at some of this funny syntax. Before we look at function templates, though, let's take this source code here. I'll copy and paste it, and we're going to open it up in a compiler explorer, which is essentially where we can put in some C++, and we can have a look at essentially the assembly that it craps out, right? So what's actually in the binary. So you compile this to a binary. The binary is basically an encoding of all these different assembly commands that are ready to be executed on an x86 machine. Okay, so this is a binary ready to go on a x86 instruction set, and you can see it's a fairly, there's some real garbage here, but you can see the basics in terms of you got a function here, and you have another function here, and then you have a main function down here. It looks really long and scary. That's not the whole main function. That's the main function, and that's like the program. Some other interesting things here while we're exploring, just refreshing your memory. So you can see here that the actual hard-coded string is actually stored there in the binary. So that's basically where this is stored, right? So again, you probably, if you haven't explored this in a while, it's like, where's that question of like, where is this string? I didn't malloc anything. Is it on the stack? Is it whatever? It's like, no, it's sitting here in the source code ready to go. We got these two functions. Our min function for ints, it does its return type. I'm not a massive fan of assembly. We take our two arguments in, so int a and int b. Then the compare is like our if statement, right? And we have some jumps, and then it's essentially a conditional jump, depending on whether this condition is true, right? So that's the function. You can see it all here. Like those lines are what's represented here. Really cool tool. Fun to play around with for really simple programs. Then you can see a double one's kind of the same, except it's got different commands, which is definitely due to double precision floating points. So processors deal with floating points differently to integers. So very separate functions. And at compile time, the compiler figures out which one to call. You can actually see here that we're first calling, where is it? We're calling min int, and then we're calling min double, right? So two separate function calls, calling different things. This stuff here looks like, you can see here's the operator output being called for ints. So this is actually the assembly trying to call the integer operator output overload here. And you can see the same thing happening for the string, because it's trying to print out first the return of this function, and then this. So it tries to do the operator overload for an int, then same for the string. And you can see the same thing down here. It's doing the operator overload for a double, I believe, and then an operator overload for the string once again. So fairly straightforward. Well, I shouldn't say fairly straightforward. It's like you can kind of clearly see the steps here. There's garbage, and half of this doesn't make sense to me. And to some of you, it makes perfect sense. To most of you, it makes half or less sense, and that's totally fine. You should remember enough of this from maybe some other courses to be like, yeah, okay, assembly, it's that thing that looks hard to read. Now, we can make our code even simpler if we try to than function overloading by using function templates. And a function template is simply an instruction for the compiler to generate particular instances of a function that vary by type. So instead of doing int min for ints, instead of doing auto min for ints and auto min for doubles, I can actually say I want to do an auto min, except I'm going to replace all my ints or doubles with a t, and then above my function I'm going to write template type name t. Now this template type name t above the function is saying to the compiler, this function is a templated function. It's a templated type. And there's going to be a wildcard, a variable, a placeholder in that function that I will denote with the letter T. So I'm creating a template, and there's going to be a wildcard type in there, T. And then I give the definition, and it looks like a normal function. It's just I use T as a type. So instead of ints, instead of doubles, it's just T. T is the type I'm using here. And then this program will run perfectly fine as well. So if I open my function template 2, and I try and build and run 702, it goes 1 and 1. Okay, so it figures out how to do this. Now, again, this is a concept you might be familiar with from other languages, where you can kind of take in a generic type, and then in Java you could say, well, if the type is an int, do this. If the type's a double, do that. But that's all dynamic polymorphism. That's all stuff happening at runtime. And what I want to show you here that really emphasizes this point is let's go back to the compiler explorer and let's have a look at this piece of code. And pay attention here to how we have our main function. Sure, looks pretty similar to before. But we still have two separate min functions. We still have a min function for ints and a min function for doubles. So in the actual compiled binary, we have two separate functions, even though we only defined one. And this is where the difference between static and dynamic polymorphism really stands out, because static polymorphism is saying we want to create many functions or many capabilities with the same interface at compile time. Whereas dynamic saying make one at compile time and figure it out later. So when this code actually runs, it doesn't run a templated function, right? The C++ compiler turns this into two functions. It does what we call instantiates two different functions. So again, a templated function or a class is an instruction to the compiler as to what functions to generate. So the compiler will generate two and it'll put it straight into source code here. Now, why does it do that? Does someone want to give me a bright idea about why that happens? Why not just do what Python or Java do? It'll take 10 seconds for the YouTube to come back. My throat hurts. My water bottle was empty, but my housemate was in the toilet, so very sad. Matthew says, would the compiler complain if we gave it a type T that doesn't have a less than operator? Absolutely it would, because what the compiler is going to do is the compiler is going to basically take your type T, generate all the things that it needs, and then see if it's valid. So if I say, for instance, tried to do this with a type, what's a type that's not comparable? Say a standard vector. Say a standard vector of ints with like 1 and then 2. So you see this one will fail to compile because you'll see the errors that you're kind of used to. Besides not having hash included vector. Yeah, call of overloaded min standard vector is ambiguous. It's like, where is it? Oh, yeah. Maybe the compiler is not super clear, but it's like, yeah, the problem is that it won't work because, it's all just types at the end of the day. So Jin says it'll be quicker this way. Pink Omega says faster. Surush says resource management. Devansh says less code. So I don't know about resource management. I think that's a good guess. I think the rest of the answers are probably accurate enough. I think the biggest one, though, is speed. Jin says it's quicker this way. Pink Omega says it's faster. And the reason for that, it's very simple. It's because you aren't having to do a check at runtime. Because what actually happens when you have a program and you say, I want to create a standard vector of ints, the compiler goes and generates an entire function, like a class for a vector of ints, all baked in, ready to go. It's like a pre-made package for that particular type int. And that means that when the program runs, it's just like, oh, create this class, made that class. It's not like create this very broad generic class and then have to do some type checking and type conversions during runtime, right? It's basically less runtime checks. And that's a big part of where performance comes from. Deep Boy 1990 says, because it's safer. Well, it's also probably definitely safer in a type checking ability, in a type checking sense, because we always want to move things to compile time if we can, right? And moving our code to like a compile time type checker here is absolutely going to give us some better certainties when it comes to safety, because any type incompatibilities will be known to us at compile time. It won't be determined at runtime. So again, this performance boost comes from being able to generate different instantiations of the same template, because template's an instruction for the compiler to generate copies of functions, so that when we run the program, it's just like call that function. No type checking needed, nothing needed. It's all ready to go for that particular type. So it does create more code sometimes, which we'll talk about, but it's also faster. Now, I mentioned this before, but some very straightforward terminology is that when we define a template, like the min function, the t is what we call a template type parameter, and the actual the list of type names is what we call the template parameter list. So they're just two really helpful pieces of, I guess, language to use. Sam says, will portability be another advantage of creating templates? I think portability is an advantage of polymorphism in general, whether it's static or dynamic, because yes, it does allow you to reuse code, essentially. Richard says, assuming this may impact the size of the compiled code. So Richard's very correct there. So when you're using C++ templates, it will increase the size of the compiled code because you're actually basically creating a function for every type that you use. So instead of just creating one like mono function, massive function that can handle any type, we're now creating like two little ones, really ready to go really fast. And yeah, it does have an impact because the size of your binary is going to be bigger. And the compilation time would be finitely longer. I don't know how long. I have no idea. But yeah, your binary is going to be bigger, which most of the time won't matter. People would often probably prefer bigger binaries to slower code. But, you know, that being said, there's lots of different applications, you know. There's lots of scenarios where you might be running C++ on a high performance, low memory, chip or something where you just don't have the kind of memory to store a giant binary or something like that. But generally speaking, it's not a massive concern in the majority of use cases. FPGAs, all that kind of low-level fun, compeng, elec kind of stuff. So the next topic is this is a bit of a weird little segue, but it's kind of interesting. Just to get the syntax down of templates. So we saw in the previous example that you can use templates by saying template type name t, and template specifies that this is an instruction to generate as many of these as you need. Type name t is the wildcard that we use to know what to generate, and we said before as well that this is called a template type parameter. That t is a template type parameter. There's actually another thing we can use here, which isn't just t. So this is a template type parameter, and this is what we might call a template non-type parameter. Now, the difference between a type parameter and a non-type parameter is actually really simple, and you can notice it pretty quickly. A type parameter says type name and then a type, like a t, a wildcard, a variable, if you will, for a type. This one here has a type and then a name for that type. So again, it's kind of like the wildcard here is actually a type. The wildcard here is kind of a variable, like a value. So that's why we call it a non-type parameter, because it's basically representing a value. Now, here, if I have a function that I want to find the minimum in an array, right, like a STL array, say. An STL array, so I pass in a const standard array. Sorry that the constness is wrong there. So it should be standard array t size const a. And it's going to return me a type t. Now that makes sense. If I have an array of type t, so I have an array of ints, then it's going to find me the min and return me a type t. It's going to return me the smallest one. And yes, in this case, it's going to copy it out. That's okay, because we're probably going to be dealing with some pretty simple types, like primitives, like ints or doubles. And you can see that, also C star for loops. Oh no, I'm going to get hit. Yes, that's right. So you can also see here, it's like we're looping through the array and we're keeping track of the minimum. And if we find the minimum here, then we return the minimum. Very, very first year style function. Oops. One thing that we've done here though, is we've actually encoded the size. Let me take this code and show you what it looks like. I think I might be potentially confusing people in a sec. So if I take this code and I get rid of the non-type parameter, like this, then you can have a find min function that takes in arrays of size 4, for instance, like this. Okay, and let's say all of all of our arrays have to be of size 4, like that. So now your function is ready for any kind of array of some random type that's of size 4. Okay, so it's generic in the sense that it can be any array of size 4, any typed array of size 4, but it has to be size 4. So this code here would work if I try and run it. Okay, min of x is 1, min of x is 1.1. So I found the min of those two things. However, what happens if I want this to be more generic? What happens if I want this to work like this? Well, I could try and change that number from a 4 to a 3, but now let's look at what happens when I try and compile it. I'm going to get an error, and the error here is saying there's no matching function call. Now this makes sense because think about how C++ works. You make a function call and it looks for a function with the same name that takes in the same types. Now, even though an array int3 looks a lot like an array of t4, it's not. They're different types. A standard array of int3 is just different to a standard array of t4, of int4. So the compiler here literally just says, sorry, but I can't find a function for you here. I don't know how to find a function where the type of x is a parameter. It just doesn't exist. So that's where we can use non-type parameters, because I'm now going to say, you know what, let's use, what was this before, standard, let's go back, standard size t size. I'm going to replace all my 4s with this variable size. Except instead of size being an argument, which would not make a lot of sense in this scenario, I'm going to actually say it's part of the template parameters. Very interesting. So it's kind of like these two are now wildcards. It's just that this is a type and this is going to be a value. Because that's how the array works, right? Like when you create a standard array, the first one is a type, the second part is a value. So that's what I'm going to say there. Now, this will compile again. And it will print out everything fine because it can match that type. So when I call find min with x, it says, oh, okay, I have a standard array int3. Does this satisfy this type here? Yes, it does. I can replace t with int and I can replace size with 3. Okay, a couple of questions. So Alex says, can you do min equals a0 instead of t min equals a0? No, because you need to give a type to any variable name. Yeah, you need to say t. Every name needs a type in C-style languages. Do you need to specify the wildcard? Are you talking about when the function's called? Oh no, that's the same question. No, you need to specify the wildcard because every name needs a type. Firestin says, so we can't do standard array t, standard size t. So no, so the question is, why, can we do that? And the answer is no, because that's just not how standard array works. So most of the time you've put something between those brackets. It's been a type, but not every STL container is like that. In fact, let's go have a look at like standard unordered set, right? So if we go look at standard unordered set, you can see here that it shows us that it is a templated class that takes in 4 things. It takes in a key, unordered map, sorry, that's what I meant. This one takes in a key and a t, and then it can take in more stuff if you want. So if you've worked with an unordered set before, which you probably have in assignment 1, you know that you can give it 2 types, right? So that first 2 are types, whereas if you look at something like array, and you have a look at these, notice that the first one's a type. The second one, though, is basically a value of n. So n is like a wildcard here, like it's looking for a number, not a particular class type. So you can't do that just because this is looking for a value. This is a non-type parameter, and this one's a type parameter because we've already got the type here, Suresh says, can we not write standard size t directly into the argument? So yes, you could add a standard size t here. You could say, all right, there's also like a size here. But the problem is the compiler, even if you specify the size here, still needs to know the size of your array to actually have it as a valid parameter, right? Because every array has a fixed size, and it won't compile if it doesn't actually know that size. So yeah, you could pass it in as an argument, sure. But yeah, it's like, it just makes things a little bit more complicated. Alex says, what I meant was, why can't you... Oh, auto-min. I'm sorry, I missed you before, Alex. Is like, can we say this? I don't know. Let's try it out. What happens if we use auto instead of t? Works fine. A little bit harder to read, I think. I think it's really good if you use templated types to really specify where you're using it. But that's just probably personal preference on my part. Devansh says, can you typecast something with size? You can't typecast something with size. So I just want to go back to the slides here. So the important thing to point out here is that type parameters are types. Non-type parameters are not types. Non-type parameters are known types with an unknown value. So when you ask a question like, can I typecast, can I say, auto j equals size 4, that doesn't make any sense. That's like saying auto j equals min 4. Min is a value, size is a value. A non-type parameter is a known type with an unknown value. A type parameter is an unknown type. So just very different there. Size is a value here, t is a type. We're using size as a value. It's used as a value here. It's used as a value here, etc. So yeah, that's all quite important. Why do we want to do this? Why would we want to put a non-type parameter in there? Why would we not just hard code a bunch of different arrays? Well, the reason here is kind of twofold, right? One is that this function now works with arrays of any size. So, it's nice and dynamic. You can use arrays of size 5 with doubles. Like, you can use any size array, basically. The other thing that's good is that sometimes you can get these interesting speed ups in your program because you've actually hard coded in those values at compile time. You've actually made it so that inside this compiled function, and we're not going to be able to see it here because the code's probably too complex. Inside our find min of ints, where would it be? Yeah, you can actually see this here. Where's that less than size part? I'm no expert at assembly. Someone else can probably see it, but yeah, I wouldn't feel confident. I have a couple of guesses, but I wouldn't feel confident pointing out exactly what it is. But essentially, the point is that you're actually hard coding the value right into the function now, so that at compile time it doesn't have to go and you're not passing it in via a function call and putting it on the stack or whatever. It's like, no, it's actually baked into the actual assembly here. Pink Omega says, can we have something like an unknown type and unknown value? No, that doesn't really work. And also the other question was, would the course prefer t-min or auto? It doesn't really matter. Not too fussed. And yes, as I've just said before, when you use type parameters, like non-type parameters here or anything, we create an instantiation of this function in the assembly for every type of that. So if you have an int array with 3 elements, an int array with 4 elements, an int array with 5 elements, a double array with 4 elements, that's 4 separate functions that will be added to the binary after the C++ compiler is done with it. The thing we need to be careful of here, of course, is how many instantiations are actually generated with this. It's probably, again, not a big issue because most of the time these days, the size of your binary is not a massive concern. Compilation time is probably a bit of a concern, but generally this is only a problem when you are dealing with something of... like dealing with such a wide array of things. Like literally if you're generating standard arrays with 1,000 different sizes of 100 different types. Like, sure, now you're going to be adding 30,000 functions to your binary. You'll probably notice that both in terms of file size and compilation time. But for general day-to-day purposes, most of the time, your templated functions or classes are not going to have that big an impact. So it's something you need to be aware of, that it does make your binary bigger, but it's not something you need to stress about. Okay, class templates. Let me just see how we're going to go with this topic. Okay. So class templates. My throat's starting to kill me. Most of the time that we deal with templates in this course is actually going to be dealing with them as classes. Very rarely do you actually want to use templates for functions. And in fact, a lot of the time, and I don't think you'll even come across these much in the course, you don't even need templates to like do this. Ever since C++11, I think you can pretty much just use auto here. So this also works fine. So auto really changed the motivation for this for function templates. We mainly show you function templates because they're an easy concept to understand, right? Functions are very simple comparatively, but generally speaking, we don't, just use auto for function templates or explicitly overload them if the behavior is not identical. You can use templates too, but the majority of the reason we talk about templates is for classes, right? When we talk about dynamic and static polymorphism, it's all about class types. And they're more complex, and more importantly, they're much harder to overload than a function. A function's pretty easy, it's parameters, stuff, return. Whereas classes have tons of members and methods, and overloading them gets really complex. So for instance here, if I wanted to have two stacks, make my own stack, standard stack, COMP6771 stack, and I was to create an int stack and a double stack, that's a lot of administrative overhead to kind of have these two different types with like different types in the data structure, different types in the parameter list, different return types, all of this kind of different stuff. So we want to use templates to try and generalize these, really use generic programming here where we need it the most. This stack class makes sense, right? You've got public and a bunch of methods, and you've got private, which stores your actual data. But how would we actually go about making a class template in C++? Well, I should have an example here. So the way we go about making a class template in C++ is pretty similar to making a normal class. You're just going to see the variable t around here. I'm going to come back to what's happening here and towards the end, but for now I'm just going to put this here. So this is a templated class, and this is kind of the beginning of stuff that will become a fairly relevant part of your life for the next few weeks. But it looks like a normal class. It says class stack, it has public, it has private, but we put a template type name t at the top. So remember, template again is saying, okay, compiler, what you're about to see is templatable, and it's an instruction that you can generate many of these if you want to. And then type name t is saying one of the parameters that we're templating this type across is a type called t. It's an unknown type with no value, t. And then we have a bunch of functions. Now most of this also should hopefully click in terms of, okay, instead of having a standard vector of ints or a standard vector of doubles, I'm now just going to have a standard vector of t. And instead of saying, okay, I'm going to push int or double to my stack, I'm just going to push t. And instead of saying my top is going to return a reference to int or double, I say t, reference to t. Same for my overloads. This is a const qualified thing, so we have like a const overload and a non-const overload for top. And then I have an output operator that instead of printing out, actually this one's fine. This one doesn't need the template because it just uses a for loop. So there's nothing, you're not actually using, oh god, why am I so tired? You're not actually using the int or the double here. You're just using like, the compiler's figuring that out for you is the point. So these are just declarations. This one's a definition, but I've got 5 declarations of these class member functions here. I need to implement them. So when I go to implement them, things look fairly similar in the sense that I say, you know, auto push, and then I give all my function stuff and I give its detail. But the two main things you'll notice are that I have to put template type name t above every single function defined out of the scope. And I, as usual, have to put in my stack class scope specifier here to give it scope. Now, I actually find putting the template type name t part fairly logical, because you know that you can't just say auto push that, because the compiler won't know what's using that. So you have to say stack t. Now, you already know that from assignment 2 if you define things in like a CPP file separately. And similarly, because you've had to scope it with the stack scope, you also have to say template type name t, because t doesn't make sense here. Like, the compiler's not just going to figure out what t is. So template type name t, or sorry about that noise. Template type name t, or whatever type you're dealing with, is basically just going to be like above any functional class that uses it. The easiest way I think about thinking of it is you put this template keyword above every single functional class, except you don't have to put it above the functions inside a class in general that you've templated. So try and think about putting it everywhere, but you can get away with it inside of this class. Like, I don't need here to say template type name t. And I don't need to say that because it already knows it's templated type name t, because it's a member function of a class that's templated type name t. But this is the gist of this one. I go through and I implement each function. Pretty okay, I think. And then we could use that too if we want to. Yeah, let's try and use that quickly. So I've got myself a stack here. It's templated on a type t. And then if I want to use that stack, I simply say, okay, well, I'm going to hash include my library. And then I have an int main function. I'm going to create a stack, an int stack called S1. I'm going to push two things to S1. I'm going to create a stack called S2, which is copy constructed. I'm going to print out S1 and S2. I'll pop it, I'll push it. I'll print out S1 and S2. I'll create another stack of strings, and then I'll push to that stack. So let's see if this one compiles. So this one does compile, and the reason it compiles right is because it's pulling these separate templates. Now, how many templates are instantiated here inside the compiled code? Right, the answer is 2. There are 2 templates that are instantiated, one for int and one for string. So again, you have to reflect the way that the compiler works here is that the templated functions or templated classes are not actual things to put in the binary. They are information for the compiler to put things in the binary. And just to go back to our earlier example to really drive this point home, if you have a look at code like this, we generate a min function for every type that uses it. So if I make another call to a min function that tries to say do A and B, the string, and then it does another one that's trying to do A and B, the character, like this, have a look how many we create. We create a min for ints, a min for doubles, a min for char const stars, which is strings, and a min for chars. So we generate 4 here. Watch what happens though if I just say standard cout hi. The program does not generate any min functions. So there is no min functions in this binary. It doesn't exist. Now, yes, optimizers will probably not include this function in the binary if you had those flags on, because it'll be like, that's a pointless function. But here, even without optimization, it's not going to include it because it had no instances of that template to create, right? It's like a template's an instruction ready to go. We didn't use it, so none of them were instantiated, as opposed to 4 previously. So in this case here, we generated, or we instantiated 2, one for int and one for string. And if we had another stack of vectors, of doubles, we would generate a 3rd one, and so forth. Now, the point of this slide here is mainly just to show you that this is how you would have templated functions that take in or return other... Sorry, this is how you'd have templated classes member functions. In this case, the rule of 5 constructors, copy constructors, move constructors, copy assignment, move assignment, and destructor. This is how you would have them deal with other templated stack classes. So you can see here that for the copy constructor, the copy constructor is called stack. It's inside the scope stack t, and it takes in a const stack t reference to s, and then it constructs it. So the point here is this slide's just a really useful reference for anyone who needs to get their head around how does copy construction and that work? Because the thing about templates is the part that always screws people up, and even me, is where do you put the t? Say you have a piece of code like this. It can get really confusing really quick because you'll... Sorry, one sec. Let me just get this. Okay, click, click, click. Yeah, so you look at something like this and you'll be like, do I put a T here? How do I know why do I put a T after that stack and this stack but not this stack? You get used to that one pretty quickly. Generally speaking, references to types require the T. What do you notice about these different stacks? We have 5 stack references in this line of code. Well, these 2 stack T's are classes. They are types. This stack is a function name, and these 2 stacks are obviously a private data member. Similarly here, this is a class. It's a type. It's saying return a reference to this type. This here is also a type. It's a scope, right? Scopes and types. It's a class scope. This here is also a type. These are data members. So generally speaking, if you're dealing with a type, then that's when you need the template. Cool. Are there any questions about this so far? We're going to take a 5-minute break. I need to drink some water, and then we'll keep talking more about templates and just lots of different things about it. Shouldn't take the whole 2 hours, hopefully. But yeah, any questions about templates? Can do some questions before the break. Maybe you're all dead. Matthew says, is there a difference in binaries for templated functions and autoed functions? No, there's not. So they're all just instructions for the compiler to generate a function, and there's no difference between them. I don't think you wouldn't be able to tell. Okay, so in the examples I gave, no, there is no difference. In other examples, so let me show, so if we do this, I'll probably try and demonstrate this. So if we do this and I replace these 2 autos with T, if I do this code will compile. Okay. One thing you have to be careful about in using autos is that autos, if let's say, watch this. If I try and say, let's tell the difference between an int and a double. So if I try and find the min between 1, an integer, and 2, a double, then what we'll end up with here is a compilation error, because basically it's trying to deduce a type of T here, but it can't, because it's sorry, you're trying to call a function with 2 separate types, but I've found a candidate function. It's just that it only takes in 1 type. The one difference you have to be thoughtful of with auto is that auto will allow things to compile in certain circumstances, like this one, I believe, not this one. Oh, wait, no, sorry, let me get rid of that. Maybe, I think it's this one. I'm pretty sure this one works fine. Yeah, it does. So you can see this one actually compiles because auto is kind of resolved on a per argument base or per parameter basis in this case. There's no way to kind of, at least that I know of, specifically be like, yes, let's let's say that this certain auto, these two autos have to be the same type. And Nathaniel's typing in the chat at the moment, and I assume that he's probably, maybe I can be one step ahead, but I don't know. But essentially, the second one we've just written, yeah, that's good. Now I don't have to, this is what I wanted to write, but now I don't have to think about it. It's basically the equivalent of this, except the return type, I guess you could leave as auto. Yeah, it's like kind of like the equivalent of this. It's like saying I've got these two wildcard types that should be deduced at compile time, but they're separate. So in this case here, if you just had this as well as a template, this would be able to compile with two separate types there. But this assumes that the two types have to be comparable too, right? Because remember, like, everything in C++ is just bootstrapped on top of each other. So if I try and say, what's the minimum of 1 and Hayden, it's going to be a compile error, because even though it'll find a candidate function that the parameters type match in, the problem is it won't be able to actually build it because it can't compare A and B. And you'll probably be able to see this here. Yeah, comparison between pointer and integer. It has no ability to overload those two things. It has no like relational operator that it can apply to those two separate types. Generally, we shy away from macros in C++ just because there's so many powerful things that can be used. Afan says, can't we use another name for the different entities? Like, why are we using stacks for all of them? I'm not too sure what you mean by a name for the different entities. The point with a stack is that it's the same. It's a container of elements that can be made up of anything. Typically, you use templates where the type is somewhat irrelevant or at least it's largely acceptable. So there's a reason like a vector is a templated class, because you can have a vector of literally any type because it's not really operating on like a type, right? Like a vector's not doing much with your type. It doesn't really care. It could be an int, it could be it could be a Euclidean vector. It could be a vector of Euclidean vectors. Like it doesn't really matter. So that's most often when you find templated class types. Anyway, let's take a 5-10 minute break, and we will keep going and start moving into inclusion exclusion principle next. So yeah, let's take a short break. From the break, I nearly forgot to fill up my water bottle, thus defeating the point of the break. Okay, well, either you're all tired or this is all making sense so far. Hope it's the latter. Templates, sure, I get it. We get it. It's kind of whatever. But one thing you might have noticed in the previous slide was that at the bottom of the .h file, the class temp main.h file, there was this little line here that said #include demo705 class temp.tpp. And then, right, it was used right here, right? That's where I included it. So it was basically just another C file. Now, conceptually, this is just an extension of a .h file. Like, imagine it's like .h file main, and then there's like a subpart that I've just like pasted in. Because remember, in C, #includes are literal copy and paste, precompile. So, why did we do that? Well, for the sake of the demo, I just copied and pasted them in so we could see them in the same spot. But watch let's have a look at what happens if I try and separate that out. So because of assignment 2, at this stage in the course, you should be familiar with, okay, I've got a main function or a test function that's actually executing. I've got my HPP or my H file that's the library. And then I have my CPP file that's attached to the library, and I compile those two CPP files together. Now, why do we, we do that to help. We do that to speed up compilation. We do that to help separate things out. But we struggle a bit with that when it comes to templates. And I'll show you why, right? I might even just use G++ for this because it'll be a bit easier. So let me just make a random folder inside of week 7 lectures. I'll call it inclusion, for like inclusion exclusion principle. And then let's make a few files in here. So first file I'm going to make is, I'll make min.cpp, main.cpp, and yep, so I got min.cpp. Alright, well let's get that in. So min.cpp is a really simple program. Let's make another one. Alright, VS Code. I'm pretty sure they can hear me. Not that me telling you that helps. Sorry. Someone will tell you that they can hear me. I don't think anyone's been listening to me for 3 or 4 minutes without saying anything. And then I have min.h, right? So I've got these 3 files. Now, these make sense. I will need to hash include min.h here, like this. And I will need to hash include it inside my min.cpp. So again, this is the model that you might have been following when it comes to assignment 2. Does someone tell me, is that columns? How do I, great, can I do another one? Perfect. Oh, that's the same file. That's not what I want. Okay, min.cpp. So here's our 3 files, right? I got my .h, that just as a prototype, and then I do a definition in my CPP, and I do a my executable main function in another CPP. Now, it doesn't matter if this is classes or functions, it could be the same thing. The same rules apply here. Here's the problem. When I go to compile this, if I go into lecture 7, and I go into inclusion down here, and then I go G++, I know the text is really small. If I go G++, -o, inclusion, and then I give it the 2 files, main.cpp and min.cpp, that's how you compile things, and I run it, we get an error, which I think is the error we expect. Yes, okay. Which is undefined reference to int, min, int. Now, what this is saying is that when it tried to compile the main function as part of main.cpp, it failed to find a definition for the min function. Now, the critical thing to kind of understanding here is that a template definition, a template declaration, just like saying min ta tb, is in itself not an instruction. It doesn't mean anything because the compiler actually needs to know at compile time what the definition is. And I think some of this is written in the slides here. So when it comes to templates, we need definitions included at compile time. Okay? They can't be instantiated at link time. Now, if you've forgotten the kind of classic model of computing or whatever, and I just, say I comment these out for a second, I think this is really important to drive home. If I create a min function like int a, int b, like this, okay, and then I'm going to create a definition of that min function, int min, int a, int b. That simply just does, return a less than b, a, b, like that. And then I call min here like that. I don't need a template because it'll look for a min. It'll find that match for me there. Now this will compile. No, because I didn't compile it properly. What didn't I save? Did I not save these files? It will compile, right? Because what does the compiler do? It compiles main.cpp and min.cpp separately. And all a compiler needs to compile a function is just the declaration. It just needs to know what's the return type, what are the parameters, and that's enough for it to say, okay, I get how it works. I will link the definition up later. I can because every file's kind of compiled in a vacuum and then linked up later. The problem is when it comes to templates, we don't really have that luxury. It's just not really how the compiler works. So when I say, for instance, here that I have a min12 and it includes min.h, which remember, for compilation reasons, is basically CPP, the main.cpp gets compiled by basically copying that in, right? So this is the file that has to compile in a vacuum. But the problem is the compiler will not instantiate templates into functions. It will not kind of generate all these functions unless it knows the definition. It needs to know these definitions at compile time. So this here won't work. Like this won't work here. But if I was to say put the definition in there, this will work. In fact, I don't need the min.cpp anymore. Right, so the whole point is that you need the definition of templates at compile time. And I'm stressing, I'm separating here compile time and link time because they are two separate things. The downside of this is that we have to expose implementation details in the .h file. Now, you can put it all inside the class body. You could put it at the end of the class body like we did in this example here, how we kind of made a class body, and then instead of putting it in a separate CPP, we just put it right at the bottom. That's totally fine. The one thing that this does do is it does slow down compilation. Because if you have, say, 10 different, imagine you have 10 different CPP files, right? And they all use a min function of ints. Remember I said every file compiles in a vacuum and then is linked back together. So if you have your entire definition, I'm going to sneeze, I'm sorry. Woo! If you have your entire definition inside of the .h file and that's included into every 10 of your CPP files, and then they're all compiled separately, you're essentially asking the compile to instantiate the same function 10 different times. So there is a compile time performance overhead to this. Right, that's the important line to stress. This doesn't make your program slower, has nothing to do with, like, nothing we've talked about today. Templates make your programs run faster than if you were to use dynamic polymorphism, but like generally speaking, your programs like don't run slower because templates exist, as opposed to defining things separately. It all runs the same in the end. It's all just about how fast does it compile and how easy it is to read and write the code. So because of that, we have to put out all of our definitions in the .h file. Okay, so you've learnt kind of an understanding about classes and like a .h, a .cpp from assignment 2. You just have to understand if you're dealing with templates, you need to put those definitions inside the .h file. You can still do things outside of the class. This isn't about whether you put a definition in a class or out of a class. It's literally about what file you put it in. Another way to do things, which we don't really recommend, is called explicit instantiations. I don't even want to really demo this, to be honest. This has been in for a while, and this has been in for a long time, and we've kind of mused about getting rid of them. But essentially, you might run into this as instances where if people really do want to keep the definitions separate, then you can essentially force the compiler to be like, hey, this is definitely the template you should create. Because there's a whole topic that we haven't really kind of chatted about, which I think we chat about at the end, which is like, how does the compiler even know which ones to generate? Like, the compiler just looks at this here and it just figures it out. It just figures out what the type is, and it just goes and creates a instance of type ints. And just to really drag this topic on, it's like a question you should really ask yourself is like, well, you know how vectors work, right? You have a vector. So if I include vector and I say auto v equals standard vector ints 1, 2, 3. Well, what do you notice here? Well, in this case here, I have to specify that it's a type int, right? I have to actually say this is an int for this to work. It's like, why don't I have to say this here? Why don't I have to say that it's an int or an int? I guess just int. Like, why do I not have to do that? We'll kind of chat more about that later, but the compiler can deduce things sometimes, right? Like, the compiler's pretty smart. It's like, well, what should this be? Well, this is going to be the type of these two things, so I guess it's that. Anyway, the point of me mentioning that was just that sometimes you can be explicit to the compiler and tell it what that is, but you largely don't need to worry about this slide. This is a technicality point here. I'll just answer this question. So Fireson says, since auto is kind of the same as template, will all autos also have to be defined in the same file? I don't know. I feel like there's an easy answer to that. My brain's not. Yeah, yeah, yeah. So basically, just to really make that question easier, if we got rid of this and we just said auto, auto, auto here like that, this would need a definition to be able to work, I believe. But generally speaking, it's like you don't have to worry about explicit instantiation and you know, putting in any things like this to explicitly say I need to instantiate these. You can just stick with what we've told you, which is that your definitions need to be in the .h file. And I think just to stress, so it's like, since auto is kind of the same as templates, it's like the way I think about auto is like auto is, as far as I'm concerned, and Nathaniel might have some opinions if he's floating around the chat, but it's like auto is really a way to simplify your source code and remove benign or unnecessary typings. I wouldn't go so far as to be like, you know, auto and templates are the same thing but different ways, because templates are a way of essentially creating type wildcards where you can say, like a class like this, where you can say, oh, well, I'm going to generically say that the stack has a variable type in it, but I expect that type to be the same in here, 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 and here. Like, if you just kind of littered auto throughout your code, you'd be making functions that could compile under a whole range of conditions. So there's more constraints you can apply through the use of templates, because you're essentially saying this has these my references of these types all have to be common, whereas auto is something that's resolved at an expression level. You know, there's no, you can't establish as much structure with it. So auto is very useful a lot more in like a function sense. And as we've said before, you don't really use templates in the context of functions. We just encourage you to use auto or function overloading because they're quite simple typically. The main use case for templates is classes, which you would struggle to use auto in generally. So one of the last kind of technicality points of inclusion, did I say inclusion exclusion principle? What in the hell have I been talking about? I'm sorry. What is that? I feel like I learned that and then suppressed it, and then I've just started saying it today. I didn't bury discrete maths deep enough inside my brain, apparently. I'm really sorry for anyone who's had to listen to me say that. That's terrible. If I've said inclusion exclusion principle, I've meant inclusion compilation model. I'm sorry about that. That's quite funny. I just went to read the title again and was like, oh, what? So the last thing about the inclusion compilation model, beyond all the other things we've talked about, is that there's this notion of lazy instantiation, which essentially says only member functions that are called when a function is used are instantiated. So what this means is like, okay, so you have a function template for min. When someone says min of int, it goes, oh, I'll generate one for you up there. And when someone says min of double, it goes, oh, I'll generate a second function up there. That's really simple because functions are just a thing, right? A function is just a unit of the thing. But a class is more complicated because a class is a big box that has a series of function definitions, and then it has like some data members in it, right? So it's a big box of stuff. And what lazy instantiation rules say is that when I create this box for a class, you know, like a stack of ints or a stack of doubles, I won't go and create a function for everything. I won't go and just create a constructor, pop, push, and everything else. I will only create what I see you use. So in this case here, we've got this like template for a stack, say. And what's essentially being said here is that if someone comes along in a main function and does this, right, stack int s, the compiler will look at this and it'll create an instance of this somewhere, right? It'll replace all of the t's with ints, right? So it sees all the t's and it goes, oh, that's an int, and that's an int, and you know, that's an int, and like this is literally what the compiler does. It's like, yep, and that's an int, and that's an int. Great. And now I've got my class, my concrete class, my instantiated class, but now it says, hey, I can see that someone's only really using the constructor and push So I'm not even going to bother adding that pop function to the class. We call it lazy because typically in computer science, right, lazy means that it doesn't do something unless it has to. Like by default, it tries not to act until it has a motivation to act, and then it will act. So in this case, what that's saying is that it will only, instantiate it once it can see someone's using it. It's not just going to go and create all this stuff for fun. What implications does this have? I have no idea, to be perfectly honest with you. Obviously, it's going to make the binary smaller somewhere. Like, it's going to avoid unnecessary binary bloat. I know that's the technical reality of it. I don't know if there's any real practical, real-world implications. I at least haven't been exposed to them personally. Firestein says, would this only apply to template classes or classes in general? It only applies to template classes, and the reason for that can be conceptualized pretty straightforward, because with a normal class, you go and actually give the definition here. The compiler doesn't decide what the compiler doesn't decide what this does. Like, okay, so let's say this is a class. Like, let's call this int stack. The compiler doesn't just say, oh, they're not using a function in their int stack class, therefore I will omit it. What's actually happening is you have a template up here, right? Like stack t. And when you use it, this might have 3 functions in it. The compiler will say, oh, they're using that one. They're not using that one. They are using that one. So when it goes to create, right? When it goes to create a stack of ints like this, it says, well, I'm only going to create 2. So my point is that it's not a compiler deciding what to ignore about a concrete class. It's a compiler deciding what it should build a concrete class with from a template. So the question of would this only apply to classes in general? No, it doesn't, because the compiler, once it has a class, does not just decide what to include in the final binary, right? It includes everything. The question is all about how much of it comes down from the template while it's creating it. And just for completeness, Nathaniel commented on my comments earlier, saying it's harder to spot bugs sometimes because if you have a typo in a function but you don't test it, you won't know until later. Yeah, so basically it's like in this case here, if you have a typo or a bug or something inside the pop function, the compiler might just not bother instantiating it, and therefore it won't try to compile with it, and therefore you may miss bugs. So sometimes you might actually write code that you think works because it compiles until you actually use it, which triggers the lazy instantiation to actually add it to your concrete class, and then you get a compile error suddenly. So I think that's a great tip. Thanks, Nathaniel. Okay, what do we got left? Static, friends, const expression, and that's it. So a couple of tidbits about how this plays out in other parts of code. So firstly, how do templates interact with static members? Static members, which you should know from week 3, are members that belong to a class type, not to a particular object that's created of that class type. The rules around templates and statics are really straightforward. The idea is that each template instantiation has its own set of static members. And this actually makes sense because there's one static member for a class per type. So if you have a class, there's a static member for that class. So, you say num stacks. If you have a stack or an int stack and you say num stacks is 0, there's one variable called num stacks. And it's associated with your class. If you have a template for a stack, and that template creates 4 concrete classes, then you will have a static for each of those concrete classes. So you don't actually have to overthink this too much. You just say the same rules of static and classes apply. It's just that a template is able to create many different typed classes. Sure, they're very similar, but they are unique types as far as the language and compilation is concerned. So for a program like the one we have down here, this, for instance, if I create a stack of floats and a stack of ints, in our overall program, we will have two static members called num stacks on two different types. They're not on the same stack or anything. Remember, stack float and stack int are, for all intents and purposes, totally different types. There's no real correlation between them in the actual like compilation model. Ints and doubles, ints and chars, like sure, conceptually they might be similar, but literally they're different. So it is just two different static members. There's nothing. I mean, I could run this code for you. We give it to you in the lectures repo. It just I think there's a little bit of I mean, let's actually see what this looks like in, just because we have a tiny bit of time here. Let's see what this looks like in the compile explorer. If I so I have a hash include for .h. I'm just going to paste that .h in here. And let's have a look at this together. Oh, my head's in the weird spot. So we have a main function here. Sure, it does a whole bunch of stuff. You can see that we call the constructor for a stack of floats. We call the constructor for a stack of ints. You can see this one is called like once because it's like a default construction. And then you can see we call some other things. There's some destructors. Oh, look, some destructors are called. Really interesting, right? Like, I mean, this is a fun thing to play around with. You're like, oh, cool. I can see that the function ends and it's starting to destruct everything for me. By the way, we're creating 3 stacks of ints here, just to be clear. Sorry. That's why we're popping off 4. Oh, sorry, there's 4. Oh, no. Let me stop. We're creating 4 stacks. One a stack of floats, 3 a stack of ints. We end up with 2 static data members because there's only 2 types we're working with. So all 3 stacks of ints, IS1, IS2, and IS3, all share the same static member because they're all the same type. If I scroll further down, you can actually see our stack of floats here. This is the constructor. This is the destructor. This is the constructor for a stack of ints. This is the destructor for a stack of ints. But what you'll also notice is, because of lazy instantiation, none of these functions here have been generated. We use the constructor and destructor. Even if we didn't define them, it would still generate them, right? Because of the synthesized constructors and destructors, right? This would still generate them. No, it wouldn't. Why wouldn't it? What did I miss? Oh, I've got the definitions down here. Obviously, we want to custom define these so that the static thing works, but these are still generated otherwise, right? They're still generated for us. But these aren't being used. But if I suddenly use one, like if I suddenly say fs.push 5.0, the compiler, oops. What's wrong? Is the problem that this is a float? is1.push, oh, it takes in a reference. Oh. When it takes, there's an interesting thing, right? Like, references are L values, so you actually can't pass an R value into this because, like, 5 is not it's not an L value reference. We're going to talk more about those next week, and my brain's going to hurt. So you'll see here, because I used a push, if I scroll further down, you'll actually see that we have... I scrolled past it, right? Where's the push function? Did I just miss it? Am I crazy? Someone tell me I'm crazy. Oh, why did it compile then? Why didn't it give me a compile error? That's weird. Oh well. Yeah, but like we could easily. I mean, the problem here is that I didn't define it, right? Like Nathaniel's right. It's like we didn't define this here, so I can just define it by copying and pasting that line and then implementing it. And how would we implement it? Well, we're using a vector underneath, so I could say stack.push arg, which should work, I guess. Stack was not declared in the oh right. Scope your classes, scope your class functions outside of your class, everyone. Don't be like me. And then push wants to take in a what's that? Has no member name push. Yes, it does. Why is it so grumpy? Oh, right. Push back. Thank you. Flex week, everyone. Yeah, so now it'll work. Should be here. Stack push. There it is. Yeah, so that's an example of the lazy instantiation happening there. Got it. So just to recap, I'm pretty sure what Nathaniel's telling me is that it was kind of compiling because it wasn't trying to actually build an executable yet. It was just compiling the file. Is that what was happening? Oh yeah, okay. So we didn't have the compiled to binary or something. Anyway, interesting tool. I'm not an expert. Just quickly moving on to a semi-related topic, friends. You were familiar with friends. Well, I hope most of you are. Because it was a topic of week 4 with the operator overloading. And the rules for friends are very similar to the rules for statics, which is that each stack instantiation has one unique instantiation of a friend. Because what do we kind of learn about friends is like a friend function is kind of like a global in the scope of the class. That's kind of how we talked about it. So there was one like friend function per class, not per like function inside the class. So, you know, you have member functions, and member functions apply at an object level, and then you had friends, which typically apply to the whole class, like statics. So it's a very similar concept here, where if we have a friend like an operator output, output stream operator overload, then how many of these function definitions do we have? Well, remember, this function is not part of an object. It's kind of global in the stack scope. Words escape me. However, similar to statics, we have an instance of this operator output stream for every single stack we instantiate. So if we create a stack of ints and a stack of doubles and a stack of chars, we're going to have 3 different operators in the source code, which actually makes a lot of sense, right? Because you're going to need an operator for each type of stack. Because, you know, the operator is basically an instruction of how do I deal with this specific type. And we can see the same thing here if I copy and paste this in. So if we have our stack here, I didn't try and compile this in advance, so I'm probably going to have some problems. Push is wanting a oh no, I misunderstood that. IS was not declared in the scope. Yes, it is. It's right there. Someone gets to point out all my mistakes for me tonight. Semicolon. That's not the problem though, is it? What's wrong with yeah, like thanks on the semicolon. IS was not declared in the scope. Is that not the name of it? So strange. Need to zoom in on this. I can't really see. I'm looking at like a smaller window on my screen. Oh, okay, there we go. Thank you. Oh, wow. Semicolons, bless. So problem there, just for context, was that this semicolon was basically tanking the next line. So when we got to this line here, line 29 never actually got like processed, right? So let's get those semicolons in. And as you can see here, right, same kind of thing. There's an operator less than overload. And how many of those are we going to create? Well, there's 2 times we're using a stack, one for a string, one for an int. So we should be able to see those as we go further down, right? We have a stack here. Yeah, okay, there's a first operator overload that takes in a output stream, a reference to an output stream, and it takes in a stack of string. This is a very long-winded C++ way to describe a string. But that's essentially saying a stack of strings, and then we'll have another operator less than down here that's like a reference to an output stream and a reference to a const stack of ints. So similar thing, even if we create more stacks of ints, even if I create like another 3 int stacks, there's only 2 types of stack that are instantiated in our code from the template, and therefore we only have 2 friends actually added to the binary. Any questions on that? Just I'll pause for 20 seconds just to check, because then we'll talk about const expression. This is a bit of a tack on the end of this lecture. Cool. A really random topic, and I think this isn't critical earlier on in the course, but it just comes up here, I guess, because we're talking a lot about like compile time and performance and stuff like this in this lecture. And basically, there's this topic. There's this keyword you can use in C++ called a const expression, and a const expression is where, just double checking, we can provide default arguments to template types, where the defaults themselves are types. No, that's the wrong text. I moved some stuff around and I missed this one. So I don't think that makes any sense. No, it doesn't. That's a separate thing we're going to talk about next week. So let's start here. So const expression, basically const expression is a keyword you use to instruct the compiler that there's a variable that can be calculated at compile time. And a const expression function is a function that if all inputs are known at compile time, it can be run at compile time. Now, philosophically, you have to think about for a second. In theory, the programs you write could be all calculated at compile time if it wasn't for unknown inputs, right? If it wasn't for waiting to see what that fetch request on the network returns, if it wasn't waiting to see what the user will input or what text is in that file. You know, in the case of Euclidean vector, it's like, well, you know, what inputs am I going to get given? In the case of word ladder, it's like, what inputs am I going to get given? But if you have a program or a part of a program or even a function in a program that is not variable or is not conditional upon some kind of input unknown to you at compile time, then it can all be calculated at compile time, which makes sense, right? Because what's one of the quickest ways to make your program run faster? It is to make it do more at compile time. This factorial example is an example of that, whereby what we're showing here is that, forget the const expression for a second, we'll talk about the keyword, but it's like, if you have, say, if you want to figure out the value of 10 factorial, I'm going to call a function called const expression factorial, which will simply, you know, do the recursive factorial call of like, you know, if n is less or equal to 1, then return 1, otherwise return n times myself n minus 1, right? If you're not familiar with factorial recursion, pause the video, go read on it for 5 minutes and come back. But fairly straightforward factorial recursion. Now, if I take this code, and I'm going to go back to the compiler explorer again, and I cut out some of this stuff. So this might be what a simple program you work with might look like. Something like this. And how this compiles is, it's like, okay, well, I'm going to compile this and I'm going to create a factorial int function. It's going to take in an int, and then I'm going to do some, you know, moves and jumps and stuff because I'm, you know, recursive, and I've got another call here. So that's the recursive call to itself. And then my main function here basically just calls factorial with an int, and it calls it with 9, which it moved into the EDI. I can't remember what that stands for. What is EDI? It's like the thing that pass it in via a parameter or whatever. So that's like, you know, that's kind of the programming model, right? Like the computers, they set things up, they call a function, the function calls itself, and the compiler turns the left-hand side to the right-hand side, which is a bunch of CPU instructions that are ready to execute this and calculate it. But think again, philosophically, about this program. The answer is knowable to us right now. We don't need to compile it and run it. It's not waiting for an input. Obviously, if we did something like we said, you know, int I equals 0, and then we said standard cin, read that into an I variable like that, now this program can't be known at compile time because we don't have all the information we need to determine the answer. So we have to go to runtime to figure it out. But in this case here, we do have all the information. Now, if we have all the information and we want to tell the compiler, we want to give the compiler instructions to basically say, hey, if you can figure this out at compile time, then do it. Then we can use the const expression keyword. Now, I'm not an expert on this, so I apologize if I get a couple things wrong here, but it's like, let me just try one for a sec. If I say like int a equals 3 and int b equals 4, and then I say int c equals a plus b, and we have a look at how this compiles, you can see that what the compiler does is it tries to translate this is a non-optimized code, so an optimizer might do something similar, but like the non-optimized code will take this and it'll try and translate it to the right here, where it will literally, say, okay, well, first I'm going to set a variable to be 3, and then I'm going to set another variable to be 4, and then I'm going to add them to, then I'm going to move them to some registers, and then I'm going to add them together. So the compiler's job is to actually translate the instructions in C code, C++ code, to assembly, to run on x86. And if I suddenly, though, put a const expression, syntax evades me, just before all these ints here, if I say const expression int a equals 3, I will get the same result because the compiler will say, yeah, I can calculate that a equals 3 at compile time. Duh, we've already done that for them. If I put it in front of the b, the exact same thing happens here, right? But once I put it, oh, it's actually done it already for me, but not with that one. Oh, no, okay, sorry. Let me take a step back. So this is really interesting because notice here, watch this like 3 here. So before, what happened was the compiler was like, I'll have to add these two registers together. Okay. Yeah, and there's so much funky stuff happening here that even I don't understand. So I'm just trying to convey the concept to you in a more tangible way, but the details get very complicated. But let me just put it in front of all 3 variables here. And what you'll notice is that, have a look at what the compiler's done here. It's basically got your 2 variables and it's like already added them in together. So I just want to be clear, like this is now saying that during runtime, set the variable c to be the value 7. It's not saying go calculate 3 plus 4 when you run the program, right? It's saying no, c is 7. You don't need to add anything. You don't need to do you don't need to run anything through the processor. C is 7, because the compiler GCC is able here to say, well, I can figure that out for you now, right now, while we're compiling. Let's do that together. And that's what a const expression variable is, and a const expression function is the exact same thing. Except if the function can figure out the value at compile time, it'll do so. So let's try this, and I'm just trying to reverse engineer this, and we will eventually. I can't remember the exact. There we go. Well, that's the only place I had to put it here. And I just want to stress again, and Nathaniel's typing in the chat again. This is one of those things where like the details really play into it. Like some compilers with certain optimization flags will do this for you. Like it will try and make all of your ints const expression if it can. So like in a way, this is a little bit like const normally. Remember how we said before that the compiler will make your variables const if it can, because it can make optimizations with const? It's a similar thing here. There are circumstances where the compiler will be able to tell that something could be const expression, and if its behavior is set to optimize, then it will set that. So by making this function up here const expression, in this particular instance of compilation, watch what happened. Let me undo that. So notice here that the way this main function worked is we called factorial online. We got the number 9 and we called factorial, and then we had a whole function here. But once I made this const expression, it doesn't even create the factorial anymore in the binary. It's gone. And in fact, that call to factorial is gone, and it's just given me the output. So if I was to run this program, this program's job is just to start, print 362,880, and then finish. That's a massive optimization. There's no recursive function calls. There's nothing like that. This is another form of compile time optimization. That's the short story. So const expression, you can apply it to functions, you can apply it to variables. If the compiler is able to, if what is it? If everything's known, if the inputs are known. Yeah, if the inputs are known at compile time, it'll be run at compile time, essentially. Yeah. It's less applicable than you think, because kind of the whole reason we have programs is for variable input, right? Like if if you can know a lot of things at compile time, you're probably solving the problem with Excel or Google Sheets or something like that, right? So don't think this is some magical secret. It's like the majority of the time, you uh, you know you can't really apply this. But you can sometimes. Now, Afan says, would it make compilation time longer though? Yeah, definitely. Well, you're just shifting computation to compile time. Um, but often that doesn't matter because often, like, compile time is usually pretty okay to be slow. Um, like the impact of a slow runtime is very broad. Like it can be user frustration, it can be lost money. Like think about think Optiva, right, or high speed trading firms trying to, um, you know, get things done quicker. Like most things really want faster runtime because it's kind of like if you think of a program, runtime time is like you being like programs like here's the problem, figure it out, there's a solution, right? And like that's it's trying to solve a problem in a certain amount of time. So if you can shorten that, the better in pretty much all scenarios. And yeah, it makes compilation longer, but it's like you can solve compilation by getting more powerful computers a lot of the time. You can do compilation offline. Pretty much the only real downside of bloated compilation, in my opinion, is uh, it's just painful for developers, right? Um, that's the main thing. But and sometimes that's a real problem. But in many cases it's like in cases where you're dealing with high performance stuff, you probably wouldn't be too stressed about speeding up compilation slightly. Someone asked what happens if the factorial is really big. Well, the I don't know, GCC will be like, I can't do that. Just like your program, if you say 5,000, it'll just complain. Oh no, it doesn't. Ooh, that's smart. I didn't even think of that. That's a good question. I never asked myself that particular question. Look at what it's done there, little cheeky thing. So in this case with the number 9, it's basically just said, oh, I can calculate it, here you go. And if I give it a number 15, it doesn't like big numbers. So, I mean, I guess the question here, Nathaniel, because he might know. Nathaniel loves C++. He's just the best. So you can see that, doing factorial of 12 and stuff did generate. Did it? Where is it? I'm lost. Yeah, it generated it for us. But once we get bigger, it seems to revert it to a function call. Does it? Yeah, it reverts to a function call. Yeah, okay. So the comment Nathaniel's made here is that, and I was wondering about this before because I didn't actually expect this to work, because normally with const expression you kind of need to put it everywhere. Like you kind of need to put it like here as well. Like your functions need to be const expression, your variables need to be const expression, everything needs to be const expression for it to work. And the comment Nathaniel's made here is that when we didn't have this as const expression before, what we're basically saying to the compiler is that the compiler is like allowed to make a const expression if it wants to, but it doesn't have to. By making this const expression, we're now telling the compiler you have to make this const expression, in which case it has failed to compile. And here, what does it said? Expansion of factorial 5, overflow in constant expression. So essentially there's been an overflow on the stack because recursive factorials are ridiculously demanding on the stack. Well, actually, I mean, no, that's not even the case. That's not even a function call. Sorry, I'm thinking of Fibonacci. It's like that number would just be ridiculously large, I would imagine. All right, cool. Great. Let's wrap up there. I think that was a fun little lecture. I hope that was a nice introduction into templates. I don't know what I said on the notice. I said on a notice today that your assignment 3 is being released at 8 p.m. tonight. That means I forgot to release it, so I have to do that right after lecture. So you'll probably get it at like 8:30. Sorry about that. So I'll release that soon. You don't have to look at it. You got other things to worry about. But we'll talk more about iterators tomorrow, which should honestly be most of what you need to start it. Because a lot of the assignment 3 is actually based on like smart pointers and same stuff as assignment 2. It's pretty similar to assignment 2, just harder. But anyway, let's wrap up there, and I'll see you all tomorrow night. And for those again in my tute, I'm gonna move it to Wednesday because I got a work meeting tomorrow that I can't move. I'm sorry. But it's all recorded anyway, so who really cares? Can you ask questions about assignment 2? I'd probably ask you to put them on the forum. I still have a backlog of some forum questions, and we'll try and get to them. It will do our best. So, yeah, I'll try and help you out there. But thank you, everyone, and I hope you have a great night. Oh, and before you leave, I nearly forgot. Oh my god, so mad. How many people have I lost already? Not many. Feedback. Can you fill out the feedback? That would be great. Thank you. And get some good feedback. 6771 feedback. Don't you love 6771 feedback? Anyway, pause the video if you want to take a screenshot. I'm not just gonna sit here. So, thanks everyone. Have a great night.